Property 2. Each chi-square distribution is associated with a degree of freedom. Okay? Nu. In one-way chi-square test, the degree of freedom is k minus 1. Where k is what? K is a number of what? Categories. In our example, A, B, C, D, E, possible answer can be one of these 5 categories. Okay? So in the question we are asking, k equal to 5. So the related degree of freedom is 5 minus 1, which is 4. In our example. Okay? In our example. And property 3. When degree of freedom increase, chi-square with new degree of freedom become more symmetric. And what does that mean? Suppose I give you a 2 chi-square test. The blue one is chi-square with what? Nu 2. The red one is chi-square with nu 1. And the question is nu 1 and nu 2. Which one is bigger? Think about it, okay? Think about it for a minute. Okay, look at here. Which one is more symmetric? Chi-square is nu 2 or the red one? Chi-square is nu 1. Obviously, the red one is more symmetric, okay? So nu 1 has a bigger degree of freedom than nu 2 because the red one is more symmetric. And this has something to do with the central limit theorem. The reason I'm not going to explain now, but when you learn to the more advanced statistics course, you will know, okay? Now, property 4. Property 4. Expected value of chi-square with new degree of freedom. Chi-square is very particular in this situation. Mean of the chi-square distribution with new degree of freedom is just nu. And variance of a chi-square distribution of new degree of freedom is 2 nu. Okay, very easy to remember. Mean is nu, variance is 2 times degree of freedom. Okay, that's property 3. Okay, property 4, property 5. The use of chi-square table. Okay, let me stop here. Now look at this is your textbook, chi-square table. It's right skew, this is upper tail. Upper tail, the upper tail probability, okay, is denoted in the table. Now, look at here, degree of freedom. We say how big is big? Well, we say what? Chi-square value is too big, but how big is big? If you use alpha equal to 5%, that means upper tail is 5%. Huh? Upper tail, 0.05, this is 5%. And degree of freedom in our case, 5 categories, A, B, C, D, E. 5 divided by 1, so degree of freedom is 4. So you move the finger this way. You stop when you see 9.49. This is what? This is the critical what? Critical chi-square value, or table chi-square value, 9.49. You get it from alpha equal to 5%, upper tail is 5%, and what? Degree of freedom is 4, okay? Sorry, I hope I did not disturb you because I just hit the computer. Okay, the use of chi-square table. This is what? The chi-square distribution, okay, with 4 degrees of freedom. And it begins from 0. We just check the table, right? Degree of freedom from 1, 2, 3, 4. Okay, 1, 2, 3, 4. And then we move horizontally. We see 9.49. Why we stop here? Because the corresponding what? Upper tail is 0.05. Okay, 9.49. That means this is table chi-square value. Or you say the critical chi-square value, okay? From the table is 9.49, and upper tail is 5%. Is 5%, okay? So we are ready to come back to answer the question, okay? We're going to reject H-snap. If calculated chi-square value is what? Is too big. But how big is big? Determined by alpha, okay? When alpha equal to 5%. This value is what? 9.49. So our decision becomes we're going to reject H-naught. If chi-square value is greater or equal to what? 9.49. Okay? Step 4, calculations and conclusion. 1, arrange the data in the form of frequency distribution. Correct answer, A, B, C, D, E. Observe frequency, 12, 14, 9, 5, 10. This is what we call FOs. Okay? And obtain the expected frequency for each category. Well, expected frequency, that means frequency you expect to see when H-naught is 2. Under the assumption that H-naught is true, A, you expect to see what? 10 times. B, expect to see 10 times. C, also expect to see 10 times. And so on and so forth. Okay? So this is our FE. This is FO, this is FE. Okay? Set up a summary table to calculate the chi-square values. 5 categories. K equal to 5. They are A, B, C, D, E. Therefore, the degree of freedom is K minus 1, 5 minus 1 is 4. Okay? 4 degree of freedoms. FO is copied and done. 12, 14, 9, 5, 10. 12, 14, 9, 5, 10. Okay? expected frequency, they are all equal to 10. So how we get the next column, the first entry in next column, FO minus FE. This is obtained by 12 minus 10. 12 minus 10 is what? Is 2. And FO minus FE squared is what? This is 2 squared. Is 4. And how we get this number? Okay, well, 2 squared divided by what? What's FE? FE is what? 10. So this is 4 over 10, that is 0.4. Okay? Similarly, we can generate what? This term for B, okay? FO minus FE squared over FE. We can, respectively, we can determine what? All the entry in this column, okay? So, how we get chi-square is summing over all possible value of what? FO minus FE squared divided by FE. So 0.4 minus 1.6, that's 2. 2 plus 0.1, 2.1. 2.1 plus 2.5, that's 4.6 plus 0. So that's why this is what? 4.6. Okay? This is a calculated chi-square value. And you need to compare with what? With a table chi-square value. This is 0. This is 9.49. When this value is greater than what? 9.49. Reject H naught. That's our decision. Reject H naught if calculated chi-square value is greater or equal to what? 9.49. Okay? In our case, the calculated chi-square value is only what? It's only 4.6. This region is called the region of rejection. This is called the region of rejection, and our calculated chi-square value is only 4.6. So, what's our conclusion? Do not reject. Do not reject H naught. Okay? Do not reject H naught. It means we retain H naught. Do not reject means retain. Okay, we retain H naught. And remember what's our H naught? The instructor shows no tendency to assign any particular correct response from A to E. Okay? So look at here. We retain H naught. These findings suggest that the instructor shows no tendency to assign any particular correct response from A to E. The difference between what we expect and what we observe can be passed off as merely as a result of sampling error, of overchance error. Okay?